This is the quality control video report for the WWC industrial chemicals, where I'll be determining whether an unknown copper sulfate solution meets the industrial specification of 0.6 plus minus 0.10 moles per liter. To actualize this investigation, I'll first outline the key theoretical concepts underpinning analytical chemistry. Presented stoichiometry, which describes the numerical relationships between the reactants and products in a chemical equation, and is grounded in the law of conservation of mass, which says matter cannot be created nor destroyed. To ensure this, you must balance both equations by making sure the number of atoms on both sides are equal. Mole is the standard unit of measurement used to quantify particles in chemistry. 1 mole represents 6.022 times 10 to the power 23 particles, which is known as Avogadro's constant, allowing chemists to relate the microscopic scale of atoms to measurable quantities such as mass. The formula is depicted as N equals to M over mm, where N is the number of moles, M is the mass of the substance, and mm is the molar mass. An example above is seen with glucose about finding the molar mass and eventually finding the number of moles. The ratio relates the quantities of substance in a reaction using the coefficients from a past equation. As represented, mole ratio can be expressed in the example. Concentration is the quantity of solute per unit volume of solution, which is most commonly expressed as molarity in mole divided by liters. It can be categorized into two subcategories. The theoretical yield is a maximum possible product, assuming the limiting reactant is completely consumed with no losses, and actual yield, which is what is physically collected after an experiment. And then percent yield is calculated as actual yield divided by theoretical yield multiplied by 100 to get success percentage. The industrial example is the contact process, which is used to manufacture sulfuric acid acting as in fertilizer production, batteries, and petroleum refining. The example of stoichiometric relationships is shown with the calculations. Therefore, the number of plant engineers to assess efficiency and identify production losses in real time, and highlight the importance of stoichiometry in industrial settings. And now for the aim and the hypothesis. One aim of the investigation was to determine the concentration of the unknown copper sulfate solution and to use a gravimetric evaporation process and to evaluate colorimetry as a replacement method. And the hypothesis was that the concentration will fall out of the 0.6 range because of the unknown concentration of the solution despite the calculated and precise processes. Please feel free to pause the video at any time. This is the risk assessment which we followed for our experiment. This is the equipment list which we used to conduct the experiment. The method we used is displayed and follows an exact and clear process. The following table represents the result which was extrapolated from our experiment. It represents the overall trend of the evaporation process. Our step-by-step process of finding the concentration of the evaporated copper sulfate solvent is shown below. As you can see, our final result is 0.46 moles per liter, which falls below the industrial specification of 0.60 plus minus 0.10 moles per liter, indicating the batch did not meet commercial quality standards. The investigation was largely valid as the independent variable, the mass of copper sulfate solution remaining after evaporation, was directly measured and used to calculate concentration. Control variables such as the volume of solution, the same apparatus, and the general heating method were kept consistent across all 5 trials. However, validity was partially compromised in 2 key ways. Firstly, if evaporation was incomplete, residual water would increase the mass and tamper with the final mass and cause the concentration to be overestimated. Secondly, the Bunsen burner produced an uneven and difficult to control heat source, which introduces inconsistency in the evaporation between trials. Validity can be further enhanced by using a thermometer to monitor the flame temperature throughout all trials to stay more consistent. The average concentration obtained was below the expected range. The major contributor to this was splattering. There were copper sulfate crystals that were ejected out of the evaporating dish onto the bench next to it. This took away from the mass or residue that was left, thus lowering the calculated concentration compared to what was actually left. Incomplete transfer of solution from the measuring cylinder to the evaporating basin may have also altered starting volumes in some trials, and an electronic balance uncertainty could have further compounded over the 5 trials, further contributing to the overall underestimation. Kept consistent throughout all 5 trials, except for one large outlier, which was 0.0385 moles, compared to the average concentration. The outlier used the largest initial volume of copper sulfate solution. However, it produced the smallest mass of pure copper sulfate. This makes it most likely that this outlier was due to either boiling the solution for too long or loss of mass when pouring solutions. A green flame was observed while heating. Green flames occur when copper sulfate is burnt, which can occur during spilling. More trials can be performed to increase reliability to further weed out outliers, creating a more statistically reliable average concentration. Several improvements would immediately increase the accuracy and reliability of this investigation. The most significant of them would be replacing the Bunsen burner with a hot plate or water bath, providing controlled heat below the boiling point and eliminating splatter, ensuring the full mass of copper sulfate is retained in the basin for weighing. Also, using a desiccator would further reduce the measurement uncertainty. This technique is colorimetry. While gravimetric evaporation determines the concentration by evaporating solvent and measuring the remaining mass using stoichiometric calculations, colorimetry measures the amount of light absorbed by the solution. In terms of industrial suitability, throughput is a critical consideration which refers to the number of samples that can be analyzed in a period of time. Colorimetry has a clear advantage here as the multiple samples can be processed rapidly using the same calibration curve. For a company like WWC, industrial chemicals that produce large batches, the speed, precision, and scalability of colorimetry makes it more practical long-term and sustainable quality control. In the table, both methods have high accuracy but have different processes along the way. Thus, the investigation determined whether an unknown copper sulfate solution met the required range using a gravimetrical evaporation method. The solution was heated to evaporate the solvent to form copper sulfate crystals. The average concentration was 0.47 moles per liter. The average concentration did not fall into the acceptable range of 0.50 to 0.70 moles per liter, which supported our hypothesis. Possible errors such as experimental limitations could have affected all the calculations effected in the experiment. The aim was fulfilled as the concentration was determined to not meet the range.